3, 2, 1. Okay. A very good evening to everyone watching and listening to this program. All right. This is the astronomy picture of the day by NASA, as presented by members of the Astronomical Society of Penang. Okay. So those of you in the world who are not aware, so Penang is a small island on the northwestern corner of Peninsular Malaysia. So we are actually to the east of Indonesia, to the south of Thailand, and to the north of Singapore. All right. So we are very fortunate today to have with the APOD session our presenters. That's myself, Dr. Chong, and Ms. Chiu Boon Wei. Okay, and our young member Marcus Cheng.
Hi.
And yes, and the session is hosted by Michael Teo, our member, and it's got the pictures are selected by our Mr. Lai. All right, so we would like to present for this month APOD for June 2023. Marcus, you're on.
Okay. So the APOD I'll be presenting is June 9, 10, and 25 of 2023. So first I'll start with the June 9 APOD. This is the Pandora cluster, which is a cluster of this cluster actually contains.
Can you share your screen?
Oh wait, yeah. Oh, I forgot my screen wasn't sharing. Okay.
Yeah, we can see.
Okay, so this is the APOD of June 9 is of the Pandora galaxy cluster, also known as ABO 2744. So this galaxy class okay, wait, first this image was taken by NASA, which I'm pretty sure most of you know what it is. ESA, the European Space Agency, and CSA. So so this is a picture of Pandora's cluster, also known as ABO 2744, and it's actually a combination of three different massive galaxy clusters. So this is actually a pretty big cluster with it's 6 million light years across. But there's actually a 2-minute video that's a tour of Pandora's cluster. The link is over here. Y'all can copy and check it out for yourself if you want. It's also in the APOD page. So like if you go all the way over here, you can go and watch the 2-minute video tour. So this galaxy cluster is actually so big. It has gravitational lensing, which is an effect that happens because gravity is actually like gravity is not just like a force that sucks you. It's basically how gravity works is um whenever any object in the universe distorts like space and time. So imagine like you put an object on the trampoline, and the trampoline would start like bending downwards. So that is basically what gravity is, and that is basically what gravity is. And if an object as big as this galaxy cluster bends it so much that also starts getting distorted, which is called the gravitational lensing effect. That's basically all I have for this. That's basically all I have for this picture. Oh yeah, and also I forgot to mention, this was taken by the James Webb Space Telescope near infrared camera. Okay, now for my next APOD, which is June 10 APOD. This is a picture of Mars and the Beehive cluster. So this was taken by Rolando Lingastri. You can see this is Lingastri. He's an Italian comet researcher. The post he made with this photo is actually here. He made a post on Facebook. It's in Italian, but basically he says that the photo was taken via SkyGems, which is actually a service that lets you remotely access telescopes from all over the world. So this is the SkyGem website over here. There are multiple telescopes that are located based in a country called Namibia, which is located in Africa. Over here, this is where Namibia is located at. It's in Africa. And he took it from one of these telescopes. I'm not sure which telescopes he took it from. There's multiple telescopes located in Namibia. This telescope, this telescope, and this telescope, and I think and these two telescopes. So yeah, there's multiple telescopes that are located in Namibia. He did not mention which one he took it with. So this is the beehive, the beehive cluster. And the beehive cluster is actually located like near the Cancer constellation, and it's close to both Venus and Mars. You can see this is a picture of Mars over here. This and But on June 12th and 13th, it would be Venus in this picture, but the light would be so bright that it would be quite hard to actually see the star cluster itself. So that's for the June 10 APOD, and my final APOD would be June 25th.
Wow, nice picture.
Yeah, which is this picture is actually of lightning on Jupiter. It was taken by NASA and wait, yeah, NASA, the Jet Propulsion Library, the Magellan Space Science Systems, and Southwest Research Institute. So the way lightning is created on Earth is through like colliding ice and water droplets in the atmosphere. And lightning on Jupiter, which is called Jovian lightning, is actually um theorized to happen the same way as on Earth. So they're actually both pretty similar, and it happens pretty regularly on Earth too. And it happens, yeah, pretty regularly on Earth. So yeah, I think that's all for my presentation. On to the I think it's time for the next presenter.
Thank you, Marcus.
Hi. So I will be presenting the next APOD, which is the 21st June APOD. So let me share my screen first. All right. So
Yeah, can see. So nice.
yeah, this is a very nice photo like taken by Marcela Gulia. So she is a very careful observer of from Italy, and he's also the astrophotographer. So her photo is mainly show about the atmospheric optical phenomena, but this APOD is actually explain our sun path changes during the year. So here you can see that this is the line that captured the sun path that captured on the summer solstice, and then below that is the equinox and the winter solstice. So this sun arc is actually captured from noon. Then noon at the highest point of the sun, and then slowly setting. So you can see that this tree path has like different length. So why is it? Is actually because as we all know that the season on our Earth is changes because our planet is actually tilted at as it actually travels around the sun, about like 33.4 degrees off. So when it tilted and rotating, right, is the different part of the Earth will be getting exposed to more or less sunlight when the planet is rotating. So this is why we have this different length. Yeah. So this summer solstice is the when the when the sun is actually at the northern hemisphere, the sun is actually has shine more time on it, and it's actually when it's a shorter no, it has a longest day of the years. Then at the winter solstice, right, it's actually normal. It's actually at the uh it has the shortest day of the year. So equinox is normally spring or autumn, right? It has actually day and night is almost equal length. Yeah. So this maybe is it will be different for the hemisphere, the north hemisphere and also the south hemisphere. It's opposite. So when spring over not no sorry at the summer at the hemisphere, then the winters at the southern northern southern. Yeah. So this this point if in summer has the longest day, the northern region, and then the southern region will be the winter solstice and very shortest path. Yeah. So normally the Earth is actually closest to the sun in January lah. So this June they actually taken in June, I think. Yeah, June 25 is summer solstice. So the sun has the longest path. Yeah. Okay. So this is taken in actually a small village. I think not. I'm not sure it's a small village or not, but it's taken in Italy. Yeah, this location. She took the picture in 2020 and 2021. All right. Okay. So I will go to my next APOD, which is the 20th of June. So next APOD. Okay. Yeah, this actually
nice.
I really feel so exciting when I see this APOD. So beautiful. Then I directly request that I want to pick this picture already. It's super. I really like this picture.
Nice.
Photo to before Beauvais, and also this line drawing is Alfonso Rosso. Alfonso is a illustrator and the character design, and the photographer Fifo is a landscape astrographer, and both of them are from Uruguay. So this APOD, right, is actually want to say that our human is so the imaginary is so creative, and then our sky is actually full of the stories behind. We actually links the stars like to become the constellations, and all the constellation like got their own mythology according to the each Asian cultural history. So most of us we know the stars or the myth are from Greek, and this actually I think this is a swan, but actually according to the APOD of today is actually Nandu.
Yeah.
And this is according to the folklore of the native people from Uruguay. So Nandu is actually biggest bird in South America. So it's a ostrich lah actually, and it's an ostrich. And then the footprint of the Nandu is always associated with the Southern Cross atheism. So they have the myth behind, and then this woman actually is a statue of the Maria Mikau. Sorry, I'm not so sure how is the pronunciation in Uruguay. So this is a statue. She is a very indigenous woman in of the Chara people who live in the 1800s in that time in Uruguay. So she is and just the symbol of the colonial resistance. So this picture, this image was actually taken in mid of April in Cabo Polonic, Uruguay. So the water scene is in the background, right, is actually the horizon of the Atlantic Ocean. Yeah, it's very, very beautiful and meaningful picture. Yep.
So allow me to add one more sentence. Bunwei is that the guy standing here, be careful, don't stand too near. The Nandu will have the dropping on you, no? The dropping. Be careful.
yeah, yeah. But really looks alive without the you see, even without the line, right? I can actually can imagine
I
of the
see.
big bird there.
Yeah, yeah, yeah.
Yeah.
So nice.
Yeah, and
Very,
this is actually the central band of our Milky Way.
very artistic. So nice.
Yeah. Yeah. Okay, so I will present to the next APOD. So my next APOD is 16. Yeah. This is also a landscape composite image taken by Bernard from the world at night. So Ber- Ber- Bernard is
Yeah.
he is a astronomical time lapse photographer from Germany. So he I think he is very famous with the photographic trip. And actually this is a time lapse video, time lapse photo that presents the serene view from the coast of the Sweden, across the Baltic Sea, and actually presenting the passage of one night in a single photograph. So actually, this picture is composite from the time step from the video, and this from here is actually you can see the time over down over there. This is the sunset time. Yeah, so it's a west, and then go to the east. This sunrise. So from sunset to sunrise, and you can see here even got the northern light.
Mm.
Yeah, very beautiful skyscape, and also the sea is actually quite peaceful because you can see it's like no wave or not wavy at all.
Yeah.
Yeah, and the composition image is you can see from the description of this airport, he used 3,000 video frame
Hui.
to composite it.
Hui.
And yeah, it's so many, and the single column of pixel was taken from corresponding individual frame and combined into sequence like
Mm.
3,000 pixels wide. So
Mm.
like very how to very detailed inside the picture.
Mm.
Yeah. Okay, so
Nice.
I will go to my next airport.
Mm.
Okay. My next airport is also my last airport lah.
Yeah.
So the last airport is the color of the universe.
Who are you?
Yeah. So yeah, very very beautiful. This is an
Another
artwork.
one. Who are
Yeah,
you?
very beautiful. The artwork from like over past 100 years or maybe longer. Yeah, because the image credit is unknown, but probably is Canal Flammarion. So this is actually appearing in a book by the Canal Flammarion in 1888. Yeah, very very long ago picture that happened in I think the Renaissance time already.
Yeah.
Yeah. So this is a very very famous artwork. If you like coloring, you can also print out this. You can also print out this and then color with the color that you like. Very very brilliant colors like the stars and then rainbow color. Also you can paint it. So the book that have been this artwork is actually from the how to say it? The book is La Atmosphere. Is actually a wood engraving. So this picture is used to represent a supposedly medieval cosmology, then including a flat earth bounded by a solid and opaque sky where ancient time they believe our earth is flat. Yeah, and also the metaphoric illustration or either the scientific and the mystical quest of knowledge. But it's actually also used to show that the humanity present concepts are susceptible of being supplanted by the greatest truth. So this picture is so nice that this you can see this man he is lying on a on the grass. I think it's on the grass. Then
Yeah.
doing the sun, the stargazing, counting, maybe counting the stars, or maybe
Yeah.
do his own uh
Mm.
own observation. So this actually what Camille Flammarion, he's actually also like, I like to encourage the amateurs astronomer to make their own observation. So you may also like find, like Dr. Zhang always like to tell us, you can find your comet, then you can name it or something, right?
Yes, yes. Yeah.
Yeah. So this is what actually Camille he proposed, and Camille he also did many science work and also wrote fantastic stories. And one of his book is named the planet Mars, and he actually support the existence of the Mars canals is built by a highly developed
Yeah.
culture. Yeah.
Mhm.
So you may find many books like from him. Yeah.
Yeah. Mm.
Okay,
So exciting. Astronomy, so exciting.
so exciting astronomy, and actually it's 1888, so that time already. So
Mhm.
very the astronomy is starting to
Yeah.
promote, science starting to promote.
Mm.
Okay, so that's all from me. I will stop sharing and pass the mic to Dr. Chong.
Thank you, Boon Boy. Yeah. So let me share the screen. Yeah. Can you see my screen, Boon Boy? Boon Boy?
Yeah, can.
Okay. Yeah.
Yes.
Okay, so June 18, okay, Saturn's northern hexagon, right? Got hexagon on Saturn. So I'll show you the, okay, let us make the picture smaller first. So basically, this is by our Cassini mission. Remember some years ago, NASA sent a flyby, what you call a rocket that passed by Jupiter and entered into orbit around Saturn. So this is the north polar region of Saturn over here. And if you look carefully, it's like a shape of a hexagon. It's so big you can put a few Earths inside. And of course, on top you see the false color image of the Saturn's ring. So of course, the whole of this Saturn is rotating anti-clockwise. So you have this. So when it first came out, you see this hexagon is 1, 2, 3, 4, 5 cannot be seen, 6. You can put 4 Earths inside. So this one is, if you look at the atmospheric dynamics, remember, this is a Saturn's atmosphere, no? The upper part of the atmosphere is quite complicated. It can be explained why you have this shape, Saturn's hexagon. And I remember I was just a new lecturer in USM in the 1980s, and this was taken by the Voyager. Was one of the Voyager spacecraft flew by Saturn and took it. This was later on, Cassini went closer to Saturn and took a better picture. So this is really amazing of the hexagon on Saturn, the northern what they call the polar region of Saturn. All right, taken by Cassini in around the year 2000, up to 2000. Okay, the next one should be June 15. Okay, so June 15, it says here. Let me see. Okay. M15, dense globular star cluster. Remember, M15 is Messier object number 15. Remember, there's a famous catalog in astronomy called Messier catalog, and it has in it 110 objects. That is actually classified by amateur comet hunter in France few hundred years ago. Wow, you mean even a few hundred years ago, comet hunting is already a very popular sport? Yeah, they find a new comet, and if they report it, confirm to a new comet, the name of the person will be the name of the comet. But this is Messier 15, okay, and it's a dense globular star cluster. So basically, a Messier object is something in the sky that looks like a comet, but it's not a comet. So this is the case. It's a dense ball of stars. So inside here, there may be hundreds of thousands of stars. Okay, Messier 15, and of course, is what they call by NASA, ESA, European Space Agency, Hubble Legacy Archive. Mean Hubble has a lot of catalog. Hubble Legacy means those that are iconic. The famous pictures of Hubble is put in the Hubble Legacy Archive, and it's processed by our Turkish image processor, Mr. Ehsan Ibrahimian. This one. And here also you have another object here, very interesting one. It's called PEAS-1, PEAS-1. Okay, it's a Planchy Nebula, just in front of the globular cluster. Right, very interesting. The next one is on June the 13th. Okay, it's a video. So I put June the 13th, moons across Jupiter by NASA, ESA, United States Agency Jet Propulsion Laboratory, Cassini Imaging Team, SSI, all right, Space Science Institute, and processed by Kevin McGill. I think one of the NASA staff who processed images. And you see the great spot here, and you see two moons. Well, basically it's like this. The Cassini spacecraft went to orbit around Saturn, but before going to Saturn, it flew by the inner planet called Jupiter, and it flew by, it took the video. So the one on the top is our Io, and the one bottom is our Europa. So you play the video now. I think there's no sound, just a video. Something interesting. How can? We thought the inner moon Io should move closer to the planet Jupiter. How come the outer one is moving faster? The reason is that the way the Cassini rocket is passing through the Jovian system is such that it moves faster with respect to the Europa than to Io. So it looks like Europa is moving faster. It's not. Actually, Io is moving faster. Okay. So this is the motion of Io and Europa above the greater spot of Jupiter, as seen by the flight by the Cassini mission, which was flew by Jupiter many years ago. Okay. Next one is June the 12th. Okay, the largest satellite of the Earth. Okay, this is very interesting. I think this is taken in daytime by our Tian Yao Yang, a Chinese. He may not, I couldn't find information on him. He may not even be an astrophotographer. It's just that he's there at the right time. He's in Shanghai City, and he saw this, and he got a camera, he took a picture, and there you have the International Space Station. There, okay, ISS, and then you have this, what they call the moon there. Very nice. So this is the largest satellites of Earth. So here you have here two. Natural satellite is of course our moon. The largest artificial satellite orbiting Earth is ISS. So in this picture, he saw large natural satellite moon, very far away, and closer to Earth is our ISS, largest satellite of the Earth. Very nice name for this picture. All right. So basically, to take this picture, very lucky lah. Right. He was there at the correct place at the correct time in Shanghai City, and he took this picture. Okay. We go to the next one, June the 11th. This one I will spend more time, maybe the longest time. Some of you may say, so what?
Wow.
So boring.
Color?
No. The sun and its missing colors. And I see here, okay, I make it larger. Okay. Nigel Sharp is basically a scientist working for NSF. NSF is the American National Science Foundation, the biggest scientific body in America. FTS, all right. This is another organization, and NSO is National Solar Observatory that runs the Inouye, the new solar telescope in Hawaii called the Inouye Telescope. KPNO, Keeping National Observatory in Arizona, and AURA is a group of big American Optical Observatory, and NSF, National Science Foundation. And basically, you look at that. Now, when I see this picture many times already, so beautiful. So basically like that. The light from the sun is collected by a telescope, and it passes through, of course, the old way is through a glass prism, but a better way is passed through a diffraction grating. So basically a grating is a lot of lines cut onto a piece of glass. Maybe on a piece of glass is about 5 centimeters in width. There are millions of lines scribed onto the surface, and they let the sunlight fall onto it and get diffracted, and you split into the colors. The long wavelength on top left, and a bit increase to the top right, and next one step down, a bit longer to the right again, and a bit longer left to right. To the bottom right is the shortest wavelength. So basically, this is all the visible light from long wavelength red, and to the right side here is blue, visible light, which is we know lah. So from the top left-hand side, 750 nanometers to the bottom right is 400 nanometers. And you see what? This is basically the solar spectrum. Another term is called the Fraunhofer spectrum, named after a famous German spectroscopist called Fraunhofer. So basically, I remember, Boon Wei, I saw in an old textbook in the USM library many years ago. I forgot the author. It's not the author of the book, but the author is he wrote that astronomy textbook. He mentioned there's another astronomer in Europe many years ago that the astronomer made a wrong comment. It's a famous comment, no? And it makes him look like a fool. That is,
What is the
no way we can understand the star. The stars are thousands of light years away, so far away. How can we know? We can only, from the light of the star, we only know, yes, there's energy from the star. No light, no energy. That's all. That's all. He didn't know that there's a field called spectroscopy, quantum mechanics. It was, so basically, spectroscopy was developed by these German scientists, Fraunhofer, Bunsen, and so on. But when they discovered the spectrum, they couldn't understand anything. They know that you have the bright background, different color, and impose on it dark lines. And they already give the names absorption lines. So basically, in the solar spectrum, I've seen in the old textbook, they join from the top left to the top right, and then go down a bit, top left to top right, down to the bottom right, into single strip of paper. Each strip is about 5 centimeters in width, but long. The whole strip, the whole spectrum is what? 50 meters long, 50 meters long. So the whole information of the sunlight is embedded in the spectrum. So when the Fraunhofer, they got the spectrum, they don't understand until the year 1900, when Max Planck came up with his quantum theory. All right, quantum theory. Remember, 1900 is a famous date in physics, in science, Max Planck discovered quantum theory, where the electron energy level are not continuous but jumps. And 5 years later, 1905, Einstein came up with a special theory of relativity. So this is an important date, 1900 and 1905. So it was only when Max Planck discovered quantum theory, and they discovered the principles of quantum mechanics, they applied to the solar spectrum, they can understand every single absorption line they can understand. So what is it? So remember, you have even hydrogen got thousands of lines, Hydrogen got one proton and one electron orbiting around it. So as the electron orbit around the hydrogen proton, it can drop to a lower level and emit a photon, or it can go to a higher level and absorb a photon. But the jumps in the energy of the different electron energy level are discrete. Similarly, all the other elements after hydrogen, helium, methane, until uranium and so on, uranium spectrum is very complex. They all follow a series of rules using quantum mechanics, all the spectrum lines. All right. So it was only when they applied quantum mechanics to the spectrum lines of the sun, called the Fraunhofer spectrum. And by the way, Boon Wei, there are scientists even take a picture, a spectrum of Betelgeuse, the bright star in Orion, and they also get a complicated spectrum like that. Also, not only the sun, of course, the sun is brighter, but even the bright star will have a spectrum as complicated as this. So basically, from the spectrum, you know how hot is the temperature of the star surface. What are the elements in the surface of the star? In what percentage abundance is the element? And what are the magnetic fields in the sun? And they will say whether the sun is pulsating or not. So riding on the beam of starlight coming from a star far away and reaching Earth, you detect it, you get tons and tons of information of the star, the spectrum. As for the Fraunhofer spectrum, the spectrum of the sun, even more information. You cannot believe what kind of information by looking at this Fraunhofer spectrum, you can get the information of the sun. Incredible, no? It's so rich. So basically, this is what? The fingerprint of the sun. Just like on a fingerprint, you touch a glass surface, our fingerprint is there. So this is a fingerprint of the sunlight, and it has a lot of information. I think I'm nothing wrong in saying that tons and tons of information. So for us in Malaysia, many Malaysians use what for sunlight? To dry their clothes, to dry their ikan bilis. But the scientists in the world will capture the starlight, just even not to say a magnitude 4 or magnitude 5 star, with a big telescope, they can get a spectrum as rich as this. So you can get so much information of the star, about the galaxy, about the nebula. Not only the star, no, even nebula, galaxy, they give off spectrum. And you have bright spectrum, emission spectrum, and the absorption spectrum. So basically, it's full of information. So maybe we should also, there are not many amateur astronomers doing spectroscopy, but some of them do. And they publish in their website the spectrum of the most of the bright stars they have, And you may say, but what's the use of doing the spectrum? The same one year after year. No. Remember, the stars are like galaxy and so on. They are dynamic, they change. The sun also can change. So some of the absorption line can change also on the sun. Some of the absorption line of the stars can change because there are dynamic events that occur on the star surface and it's seen in the spectrum of the star. Dynamic. So you see in the change in the star spectrum, you know more about the evolution of the star. So basically, next time you see a star, if your friend say, but that star is not so bright, but you remind them that, by the way, you pass the starlight through a telescope, collect more light, and pass through a diffraction grating, you can get tons and tons of information on the star. You can list out hundreds of information of the star just by analyzing the spectrum, the emission spectrum and the absorption spectrum. So basically now, I think that most of the lines here, the scientists should be able to analyze what it means. But I understand that even atomic spectroscopy or stellar spectroscopy, some of the lines of the stars are still not very well understood. But I would say that most of the absorption lines are very well understood for the sun and for the other stars. Okay, so this is really exciting. Starlight encoded in it has all kinds of information about the star. So the famous European scientists who made the statement, cannot get any information on the star while they're so far. Yeah, we see light, but that was before discovery of spectroscopy. What can we know? But now we know he's wrong, totally wrong. So much information of the star can be obtained by studying its spectrum, the emission and the absorption spectrum. Okay, so the next one, June the 8th. Okay, now again, when I see this, I was like in my mind, I say,
Wow.
boys and girls, welcome to the Astronomical Zoo. Welcome to the Zooniverse. So you have the elephant's trunk. It's quite obvious this elephant trunk. I don't very quite understand where does it. This is a caravan. Remember, in ancient time, the caravan is in front is some horses will pull a kind of a cart where there's a roof in it, and the man and woman can stay inside the cart lah. So this is a caravan, but there's no horse lah. So it's an elephant pulling the caravan, no. But this is an elephant trunk and this. So basically, this is a case of taken by Steve Canistra, website Starry Wonders. Okay, so we understand that he's an astrophotographer from Boston, Massachusetts in America, near to New York lah. And this is in the constellation of Cepheus. But because now this what you call APOD is so very well known, they will not say, okay, what telescope he used, what processing image method he used, and what's exposure time. They don't. Previously, they will give you what telescope, what exposure time, and what the processing technique. Now, no, that's assuming that you look at it, you already know about astrophotography, astroimaging. Okay, so basically the elephant trunk and the caravan, and we know it's an absorption nebula. So this is so basically this is what. So I will call that these are dense molecular cloud or dense dust cloud embedded in a molecular cloud, the emission nebula and so on. So we know that this is the case, a stellar nursery. If we wait long enough, those dust particles in space, the gas particle will clump together because of gravity. And if it succeeded that they can clump faster than they are dissipated. What do you mean by dissipated? There are some of the stars here which are very young stars, It will give off the starlight very, very strong. So if the clumping of the dust grain is not fast enough, the starlight, very, very violent starlight, the UV light and so on, will evaporate the particles of dust. So the clumping of the dust particle must be fast. So it can clump faster. Then what happens? A dust cloud is formed. And then what? A sun will be born, planets will be born. So in a sense, our solar system, you and me, and just now you ate your chicken rice, very tasty. The chicken, the meat come from there, from a kind of proto-solar nebula that collapsed like this to form the solar system. and eventually created the chicken and the drumstick you ate just now. So in a sense, this is a what? This is a birth of future star system. And you see, this part of the sky, I'm not measuring that, could be many layers in distance. So inside here, you can put in millions of solar systems. So that means what? Not one star will be formed. Many stars will be born. Many thousands of exoplanets will be born. And in future, what? Aliens will come from there. Okay. So this is our stellar nursery. Very beautiful. All right. Not only nice, but also the story also nice by Steve Canistra from Boston, Massachusetts. Okay. So the next one is June the 7th. Oh, this is very nice. Oh, where was such a thing? It's a galaxy by our, what do you call, Brian Brennan, astrophotography from New Jersey, USA. By the way, some of Malaysians not aware of American geography. New Jersey is just across the channel from New York City. Just across from New York City is New Jersey, a small state in America. So this is our M94, Messier Object 94, a double ring galaxy. There's an inner ring and there's an outer ring. So they are still scratching their head, how the outer ring formed. So basically, the inner ring is made up of what? Billions and billions of stars. The inner ring. The outer ring is also made of billions and billions of stars. But the inner ring shape and the outer ring shape doesn't look similar. And you look at the inner ring, question, how does this inner ring rotate? We know it rotates clockwise, like that. Right? Because you look at the way the lanes of the dust lanes and the star lanes are aligned. So it rotates. That means rotate doesn't mean rotate. The stars will orbit the center of the galaxy clockwise. Similarly, the outer ring also will orbit around the center of the galaxy clockwise, but at a slower speed. Was further away, moves at a slower speed. Okay, so like this. So now it seems even today, this is in Canis Venatici. Canis Venatici in Latin means the running dogs. So running dogs, we don't see many nice objects, but there's some object there, okay, called a double ring galaxy, right? And of course, there are these stars here in the foreground are inside Milky Way. And as you look through imagine your house is a house, and you look through the window of your house, imagine on the window glass pane of your house, got a lot of spots on it. So as you look outside your house, you see those stars inside your house. But far away, you see another house 100 meters away. That is this galaxy. Okay, so this is our double ring galaxy M94, okay, by Brian Brennan from New Jersey, USA. Okay, we go to the next APOD, June the 3rd. Okay, this is interesting. I remember the picture on the left many years ago. So basically this is a picture of Charon, the largest moon of Pluto. You remember Pluto, I understand they have discovered Pluto has 5 moons orbiting Pluto. So basically on the left here is a picture in 1978. The big blob here is Pluto. And Charon is this dot here, joined to the Pluto. And if the Charon is orbiting Pluto in the clockwise direction, so this will orbit now. So basically this is the discovery picture of Charon. So they have, remember the what they call Clyde Tombaugh discovered Pluto in 1920, nearly 100 years ago, using the telescope in Lowell Observatory in Arizona. Okay, and when they discovered it, then later on, 1978, they discovered this spot orbiting around, moving in a certain way around Pluto, and it's Charon. And then of course, this is, remember, there was this some years ago that the New Horizons space probe by NASA. I think one of our website group is after New Horizon. NASA sent a quick flyby of Pluto. They cannot follow the idea of Voyager 1, Voyager 2, right? Because Voyager 1, Voyager 2, they use the gravity assist effect. They fire Voyager 1, pass by Saturn, and go to Jupiter and get a kick from Jupiter, extra kick, gravity assist. And then after flying by Jupiter, it go towards Saturn and passing by Saturn in such a way, gravity assist on Saturn and the kick. So by the time they reach the Neptune, with all the extra kick, they can go there. But the thing is that By using this gravity assist, it takes a long time. So NASA have this ambition mission that they develop new horizon to fly straight at Pluto in at a very fast speed. No more gravity assist. But the problem is the speed of flyby is so fast that when it fly by, this is not Pluto, or this is Sharon. When it fly by the Plutonian system, Pluto and the 5 moon, within a few hours, it went right across the Pluto system. And it cannot enter around orbit around Pluto. So fast, and it went away. And of course, some years later, it went through by a new object called Ultima Thule, APOD. All right, that's the furthest object flown by a spacecraft by man is APOD, all right, or Ultima Thule by New Horizon. But this one, as it flew by this Pluto, it quickly flew by Sharon and took a picture of Sharon here. See a black spot here. So nice, all this. So I'm very sure when this picture started to come, so how does it come? Remember, NASA, even when they developed the program to go to the moon, they have started the DSN network, Deep Sky Network. One of the radio telescopes is in California. One of the big radio telescopes is in Madrid, Spain. One of the big radio telescopes is in Australia. So that 24 hours, they can always receive information, radio information from outside the Earth. So when they flew by this Pluto, of course, they send back to the deep sky, what called Deep Space Network of NASA, and they developed this picture. And I'm sure when this picture came out in the what? Okay, NASA, Johns Hopkins University. Now, Johns Hopkins University is where you have the Space Telescope Science Institute is based. And what is that? Space Telescope Science Institute is what? Hubble and Webb telescope. Okay, and this is the Applied Physics Laboratory of Johns Hopkins University, Southwest Research Institute, U.S. Naval Observatory. So I'm sure when this appear on the screen, those scientists who are geologists, they are jumping with joy. Whoa, very nice. How come this happen? How can this happen? So straight away they try to come up with some theory already. So maybe after 1 or 2 years, they have what seminar, conferences, then there will come some nice explanation of this. But publish a paper right? But maybe some of the discovery they make after some years, they still cannot understand the such type of discovery. So these are the latest discovery of Sharon. All right, remember Pluto got 5 moons, and the surprising thing is Sharon's diameter is half the diameter of Pluto. Our moon's diameter is much smaller than that of the Earth, but Sharon's diameter is half that of Pluto. So in a sense, you cannot consider Pluto and Sharon to be a moon. You consider Pluto and Sharon to be a double planet, a planet called Pluto and a slightly smaller planet called Sharon, and of course all the smaller moons also. So this is our Sharon, the moon of Pluto, as imaged by the New Horizons what is called spacecraft that flew by Pluto years ago. Okay, we go to the last APOD picture, June the 1st. Okay, recycling Cassiopeia. Okay, so NASA is a Chandra X-ray telescope. In optical, NASA and the Space Telescope Science telescope, which is optical. So the X-ray, all the NASA, Chandra, and so on. Optical is NASA. NASA should be, and STSI should be Hubble. So the visible one are the white color one, the yellow color one, optical light. The X-ray are the blue one. That means the normal wavelength in visible light is the white color, the yellow color, and maybe the pink color. But the X-ray are the blue color, very short wavelength. Right? So all combined together, you have this. So we know that when radio astronomy was developed, they have big radio telescope on the Earth. They point in the sky. Very in a short time, they realize that hey, in constellation of Cassiopeia, there's the brightest radio source. Remember, the stars emit radio wave. The nebula emit radio wave. Even comet will emit radio wave. So all types of radio sources. But this is the strongest radio source as observed from Earth in the sky. It's called Cassiopeia A. And basically we know that it's a remnant of a supernova that exploded years ago and is still expanding now. All right. So this is Cassiopeia A. It's the violent place to be. So don't go there. You go there, you get 1,000 X-ray picture every second, Remember, there's a kind of Malaysian Health Service got a certain type of regulation that your X-ray exposure or so much radiation is so many sieverts. They call sievert. That's a unit. Cannot exceed point how many sievert per year. If more than that, it's dangerous. But exposed to radiation can cause cancer and so on. But you are here. Every moment you have thousands of X-ray exposure. Dangerous. And also, because it's a violent place, so Boon Wei, you cannot use your handphone there. It's a strong source of radio wave. Our radio wave emitted by handphone is very weak. But here the background radio wave is so strong, it will drown out your handphone radio wave. So this is the violent place to be. Don't go there. Far away, you observe. Okay. So this is our recycling Cassiopeia A. What's the meaning of recycling? It's like that. As I said earlier, in one of the what they call dust nebula, absorption nebula, is where the new stars will be born, and so on. So basically, the same thing here. There's a star here, a red supergiant star or blue supergiant star that exploded. So when it exploded, it will have stellar nucleosynthesis to fuse the lighter elements to the heavy element. That means stellar nucleosynthesis will fuse from hydrogen, helium to carbon, oxygen to iron. All right. And during the supernova, it will fuse from iron to lead to gold to uranium. So all the elements of the periodic table are now thrown into space. And this is recycling it into space. What's the meaning of recycling? For the next generation of stars and planets and aliens to appear. So that's the meaning of recycling. But by the way, the atoms in your body, the oxygen you breathe, and you're sitting on the floor with the concrete floor with silicon, all right? Actually recycle material from the protosolar nebula. Okay. So our sun, our solar system, the planets, every atom in your body, everything you see on Earth, all right, is actually from a second generation of star that appeared after the Big Bang. So our sun, you and me, is the third generation star after the Big Bang. I mean, before the sun, there were 2 generations of stars earlier than our sun that appeared after the Big Bang. So we are third generation star after the Big Bang. So this is called recycling of Cassiopeia A. Supernova explosion that exploded years ago and is still expanding. And in the years to come, a new star system with new planets, new aliens will be formed from the recycled material created in the stellar, what you call nucleosynthesis. Okay, so that's my last APOD picture. Okay, so now I unshare my screen. Okay, Boon Wei, you're still there? Yeah. So now you can check our Facebook, YouTube. Any question?
Yeah, I see. YouTube. There's a question regarding I think the sun spectrum one. So
Yeah.
the MA asks is every star spectrum would be unique.
Good question. Let's go back to the picture. I'll be patient. I go back and share again. June 11. Wait. Oh, wow. So basically, will all the stellar spectrum will be unique? Answer is no. Because you see, we know that our sun is a yellow dwarf star, and you have our HR diagram, which is stellar classification means from when I start in the beginning is very high surface temperature. When the end is very low surface temperature. Very high surface temperature means 20,000 degrees Kelvin on the surface. Very low could be 2,000 degrees. So O, B, A, F, G, K, M, E. All right? Our sun is G class. All right. So different stars will have different stellar spectrum, the color, the bright color, and also the dark absorption line. But basically like that. Can you say that if this is a sun spectrum, now imagine I have a line here which is Fe2. Fe2 means, or Fe++, it means that iron that has lost 2 electrons. So that's what doubly ionized iron. The first iron is Fe, the second iron is ION. So this iron, what you call ion, has lost 2 electrons. So can we say that some of the stars have the iron line? Yes. Or maybe here this is a silicon line. Is only the sun got silicon line? No. Many stars got silicon line. But our sun has all these lines, but the other side, some of the lines similar to the sun, but some of the lines in the other side are different from our sun. But basically like that lah. You look at our sun is called a yellow dwarf star because the average temperature of the sun is yellow. But you look at some of the blue star, like Rigel is more bluish, more towards the short wavelength. So for Rigel, the blue part of the spectrum, the green part will be stronger. So for Rigel, the red part here will be weaker, not so red. So for Rigel is more blue, and maybe more of the absorption lines are produced because of hotter surface temperature of the Rigel, and because it's cool, it doesn't have this what you call long wavelength, so this will be weaker. So I would say unless you have two stars that are more or less exactly the same. Well, remember, our sun is classified in the HR diagram classification, Hertzsprung Russell, as a G2 yellow dwarf main sequence star. Question: are there other main sequence star like our sun, G2 yellow dwarf on the main sequence? Yes, there are quite a lot. So I can find another star in the main sequence of Milky Way, also G2 yellow dwarf, then the spectrum will be similar. Not exactly the same, 100% same, but the protosolar nebula that formed the sun that created this spectrum, and another protostar nebula that collapsed to form another star may not be exactly the same because the earlier generations of stars that collapsed may be slightly different. So the spectrum of that G2 yellow dwarf, another G2 yellow, they won't be 100% the same, but quite similar, right? So basically, you say, is it possible to have two stars in the Milky Way in all aspects, the spectrum to be 100% the same? I would say very unlikely, very unlikely. So in a sense, the stellar spectrum of our sun and every single star in the Milky Way is very, very unique lah. Just like I say, no human being in the world has the same fingerprint and the toe print as another living human being. They're all slightly different or very different. Okay, so this stellar spectrum different. Because why Bunwei, if you apply your stellar spectroscopy quantum mechanics to this, every of these 100,000 lines can be explained one, as I said, the temperature of the star system, what's the magnetic field of the star system by the Zeeman effect. So a lot of things you can study. Yeah? So I don't think so the conditions of our sun are exactly duplicated in another star in the Milky Way. So there should be differences in the spectrum. All right. No two stars have the same exact stellar spectrum. Okay. But what about our galaxy? This is for a single star, no? If we point our telescope at Andromeda galaxy or any bright galaxy, and we can split, this could be, say, a galaxy spectrum of the spectrum of a galaxy. Well, what do you mean by that? That means this is the spectrum of a galaxy, means that the lines here are not from the whole galaxy. The lines here are the billions and billions of stars in the galaxy combined together to give this spectrum of the galaxy. All right. So for the galaxy spectrum and the star spectrum, you get different information. All right. Like this. So any question or any comment from the person? Yeah.
No.
Yes. Yeah.
Yeah, I think that's the question. Yeah.
Okay. Okay. Good. So okay. So thanks a lot. Don't go yet. When Michael stop, we can chat a short while. Okay. So thanks again to
Okay.
everyone. Thanks to Apostle. Thanks to Mr. Lai who chose the picture, Michael who hosted tonight's presentation, and of course our young member Marcus and Bunwei. Thanks to Bunwei. Okay. So
Thank you.
Bunwei, we wait for our workshop coming. Okay, spectroscope and the standard workshop. Anyone can join us to do. Okay, I'll fix the date. Thank you, Michael. Okay.